good morning, actually, for you who are in California. I first thank the organizers and especially Arben and Dave for inviting me for this presentation. I apologize for not being there. I had a stupid accident just a few days before departing, and so that I had to give up with my flight and my trip to California. Thanks also to Martin and Rob for their enlightening presentations. My presentation will be mostly on an end user perspective, and the case study that I'm referring to was dealt with within a joint project that we had a few years ago with Munich Re, an insurance company in Germany, and cooperation with Marcus Tupazzini, who is probably present now and will be speaking tomorrow on the, say, more application phase of not only this study, but in a more general framework. The study has dealt with an enhanced probabilistic seismic hazard assessment in Istanbul by taking advantage of physics-based simulation of ground motion and taking advantage of different scenarios that were actually obtained by the kinematic rupture model generators that Martin was referring to. Now, sorry, let me use the laser pointer. Okay, the software, the computer program that we used for the elastic wave propagation problem, physics-based simulation, was SPEED, that was developed, has been developed for, say, more than 20 years at Politecnico di Milano. Now it enjoys some features that allow actually to perform in an effective way high speed calculations in large domains by taking also advantage of discrete Galerkin approach that allows you to put together portions of the domain with a different element size, with a different polynomial order. Now I will go fastly on that. SPEED is equipped with several viscoelastic models, also a nonlinear elastic model, and particularly for this presentation, also, of course, the possibility to inject arbitrary slip distribution models. And actually, we have implemented several of the kinematic rupture model generator that we have referred to in the previous presentations. Now, it also is equipped with a procedure based on artificial neural network to enrich the low frequency signals that are simulated by the physics-based simulations through hybrid approaches now tuned by the presence of an artificial neural network that actually allows to provide, say, realistic spatial correlations of ground motion and also realistic period-to-period correlation, especially between long and short period spectral ordinates. Based on that, and this will be dealt with in a subsequent presentation by Chiara Smerzini, we have also constructed, dealt with a number of simulation of case studies throughout the world. Okay, not in California, actually, but many sites in the world. Also constructing a data set of ground motion simulations that Chiara will be talking of later. Now, moving now to the issue that we are considering, the numerical simulations in the Marmara Sea, referring to the probabilistic seismic hazard assessment in Istanbul. Of course, this was related to a construction that all of you that are familiar with the construction of a numerical model for such physics-based simulations is very, say, demanding, not that much in terms of computer time, but especially in collecting the information about topography and bathymetry as well as regards the Marmara Sea, the tectonic context for the fault simulation, the geology and geotechnical characterization of the area, the generation along the branch of the North Anatolian Fault on the Marmara Sea that these simulations refer to, the generation of a, let us say, sufficient number of slip distribution models, and then running the number of simulations. So we started, as I was saying, we started from a digital and bathymetry elevation model with a model coming from a microzonation study, from which we classified the different areas of Istanbul based on the VS30, and then we associated to each of these classes a velocity profile as a function of depth. And then the spectral element model was constructed again with a number of, say, huge number of degrees of freedom, still much less than what they was mentioning before for exascale computing, with a maximum resolution that was about 1.5 Hertz. Okay, first of all, the validation phase was based on the records obtained in the Istanbul area from a relatively small shock of a magnitude 5.7 earthquake along the branch of the Marmara Sea fault in 2019. The comparison was rather good. Of course, the dots that you see denote the goodness of fit from the different stations for which we had the records, and then for two stations, the S1 and the S10, you can also see the comparison of the time histories that were simulated. Of course, it is a relatively good comparison that at least gives the idea that the geological model was relatively well defined in terms of the numerical simulation. Of course, moving from a 5.7 earthquake to the 7 up to the interval range of magnitude 7 to 7.5 that is our target, is not a guarantee, warranty of the accuracy of the high magnitude simulation results. But at least this provides a good feeling about the adequacy of the geological model. Then in the magnitude range that I was mentioning before, we used the rupture generator devised by one of the rupture generators devised by Rafa Shoreta and co-workers, and we constructed about 60 kinematic slip distributions that we used more or less evenly distributed in the magnitude range that you see there. And of course, some of them provided forward directivity ground motions, some backward directivity, some neutral directivity, and of course the effects, as we will see, are quite different depending on where the fault rupture occurs and where is the site of interest. Here I denoted 4 of such sites, say the old airport, Hagia Sophia, the Bosphorus Bridge, and the Princess Island, Burgazada. What was rather, say, astonishing was that, as we will see in a while, by comparing the results for the high magnitude with the ground motion models, was that while we found a relatively good agreement of the average results obtained by the different simulations that we performed for the magnitude 7, then for the magnitude 7.4, we found out that most of the slip distributions, the coupling of the hypocenter location and slip distribution, turned out to provide somewhere in the area of Istanbul to provide systematically forward directivity conditions, either in the western side of the European part of Istanbul or on the eastern side, on the Asian side of Istanbul. And this was because for the magnitude 7.4, all three branches into which we have subdivided the North Anatolian Marmara Sea fault were actually activated. And as I was saying before, you see here with the red lines, the Chu and Yangs, and also the Kautz and others ground motion models, empirical ground motion models, with the red lines, and with the black lines, the resulting attenuation of p ground velocity with the distance resulting from the physics-based numerical simulations. And as you can see, while more or less magnitude 7 are within well within the range of variability of the empirical ground motion models, a very good, say, agreement with 7.2. With the 7.4, as you can see, the black line, so the average of the numerical simulations tends to go towards the higher range of the empirical ground motion models. And by the way, by considering a ground motion model that was devised specifically for the forward directivity ground motion by Bray and Rodriguez-Marek, it ended up that, and this is the green line now, it ended up that the results of these numerical simulations were tended to agree with the forward directivity ground motions, then confirming that the slip distribution tends to affect different branches of the fault, then we may have, in general, a more probable occurrence of forward directivity ground motions. Now, how to exploit the physics-based numerical simulation results within a PSHA framework? Now, actually, in general, the PSHA framework gives you the probability that or if you want the annual probability that an intensity measure exceeds a given value as the combination of the probability of a given scenario among all of those that are considered in the PSHA times the ground motion model. That is the probability that the intensity measure exceeds that value given that scenario, if you want, given that magnitude and distance, and possibly also side conditions. Now, the physics-based simulations then can be used as either as an alternative to the empirical ground motion model. So we will have ground motion models that are site or area specific based on the PBS, or they may also be used as say, an hybrid complement to empirical models, especially for those conditions such as the near source conditions that Dave was referring to in his previous presentation. So hybrid ground motion models that take also advantage of the physics-based simulation. In any case, physics-based simulations may not be directly related to deterministic approaches to seismic hazard. As you can see here, they are perfectly fit within also a probabilistic seismic hazard assessment. By the way, these results have been say, extensively discussed in a paper that was published in Earthquake Engineering and Structural Dynamics in 2021. Now, for example, based on the vast amount of scenarios that we developed, for example, in the station, say, located in Hagia Sophia, we can construct the physics-based ground motion models by these frequency histograms that can be fit by a log normal distribution. Now, for a magnitude 7, this is peak ground velocity for magnitude 7 at Hagia Sophia based on the different numerical simulations that were carried out. So you can define a specific probability distribution of the ground motion model that will differ somehow from, say, in this case, from the Chu and Yang's, because of a slightly larger value of the median and also a smaller value of the sigma. You see the two sigmas that are indicated here. There is also here the probability distribution by the forward directivity model by Bray and Rodriguez-Marek. As you can see, it fits a coda of the physics-based numerical simulations results for the magnitude 7, while it is much closer to the results of the physics-based simulation for the magnitude 7.4 that, as I was saying, are actually dominated by forward directivity types of ground motion. Now, the issue is whether this about 20 simulations per magnitude interval are actually sufficient to capture the variability of ground motion station by station. This is, we explored this issue by considering among the about 20 simulations, this is for the magnitude 7.2 for the different sites that we have considered, different number of physics-based numerical simulation and compared to the median and sigma values, that is the moments, the statistical moment of the log normal probability function that was explored here. So we tried to see how many simulations did we need in order to have stationary values for such moments, because in that case we could actually say, okay, this is stable results and we can use it for the area specific physics-based probabilistic seismic hazard assessment in Istanbul. And we realized that about 10 to 15 simulations are actually sufficient to have not only the median values that, as you see, are really rather constant with some variability where the forward directivity in Burgazada in the eastern side of Istanbul are more evident, not only in terms of the median, but also of the sigma values. So how much this rupture generator is representative? This is something that is one of the issues that Martin and Rob were also introducing in their presentations. So, for example, how much should we be concerned about super shear rupture slip distributions and velocity models? Of course, if the probability of such super shear types of rupture is large, so we may expect, say, 30% of these slip distribution models to be affected by super shear, then we should have a much larger presence of high values of peak ground velocity, and this distribution would not be any more suitable. If instead the percentage of such models be, say, few percent, 5%, and so on, okay, we may have some spikes, some additional values of high peak ground velocity, but all in all, the overall presence, the overall, say, probability distribution would not change significantly. We also explored in Istanbul for our results the between event and within event variability. This comparison is based on made with respect to the number of earthquakes and records that were also recorded in Christchurch in the 2012 sequence, finding that the results were reasonably, in this case, in a very good agreement, actually, showing that at least from the point of view, both of the between event variability, that is the efficiency of the different sleep distribution models that were considered to provide a realistic between event variability, and also in terms of the within event variability, the results were rather satisfactory. I will finish just by saying, introducing something that you will see in the presentation by Marco Stupazzini tomorrow. We gave much emphasis in our work in an alternative approach, alternative to the defining the probability distributions, with the what we call the footprint-based probabilistic approach that essentially considers not the probability distribution at the site, but considers directly the overall number of numerical simulations for each interval range that were combined in a logic tree framework. And the results actually of the physics-based simulation, this is the annual exceedance rate in terms of peak ground velocity at different sites, as you can see, tends to be the one that comes out from the physics-based simulations, either in terms of the footprint-based or the probability distributions, is within the standard models, Chu and Young's, the red lines, and the forward directivity models, the Bray and Rodriguez-Marek. So just to finish with this presentation, we have seen that in this way we can actually use the physics-based simulation in a fully probabilistic seismic hazard assessment framework. And at least in the range that we have considered, especially in the Istanbul case, 10 to 15 simulations were found sufficient to obtain stable results. And also a footprint approach, as I was saying, is also suitable to account for the spatial correlation of ground motion. Now, thanks for your attention, and Chiara Smerzini and Marco Stupazzini today, and Marco Stupazzini tomorrow will give you further, say, insight on the work that I have just say introduced. So thank you very much.